Practical LLM, Tree of Thoughts, TOT. Welcome to the world of large language models, where the magic of text generation meets the challenges of problem solving. From crafting poems to solving equations, language models have revolutionized AI capabilities. But have they truly mastered decision-making in complex scenarios? Can AI handle problems where intermediate steps are critical to reaching the solution? Can AI generate and evaluate strategies for complex planning tasks? This is where our journey begins. Introduction. The limits of simplicity. Large language models, LLMs like GPT-4, are powerful, but fall short in tasks requiring strategy, planning, and foresight. Imagine trying to solve a math puzzle or write a coherent story, tasks where early decisions shape the outcome. How do we equip LLMs to think ahead, evaluate options, and avoid getting stuck in a single track of reasoning? Picture this: a digital assistant that can solve puzzles, write essays, or tackle crosswords effortlessly. Yet even the most advanced language models, LLMs, like GPT-4, falter at problems that demand intricate planning or foresight. Why? Because their thinking, akin to System 1 in humans, is fast, intuitive, and often shallow. This approach is fine for straightforward tasks, but struggles with challenges that need deliberate, multi-step reasoning. To break free from these limitations, researchers introduced the Tree of Thoughts, TOT framework, a groundbreaking way to make LLMs think more like humans solving complex problems. Deliberate reasoning. Infinite potential. Tree of Thoughts, or TOT, transforms the way LLMs solve problems. Imagine each decision as a branch and each idea as a node in a tree. Instead of following a single path, the model explores multiple branches, evaluates them, and backtracks when necessary, just like a chess player contemplating moves. Core concept: thinking like a decision tree. TOT organizes problem solving as navigating a decision tree. Nodes represent thoughts or intermediate reasoning steps. Branches reflect possible next steps or ideas stemming from the current thought. Paths: each sequence of connected nodes forms a potential solution. Instead of directly predicting the next token or step, the model generates multiple thoughts, evaluates their feasibility, and selects the most promising paths to continue. Step-by-step mechanism. Step 1. Decomposing the problem. The problem is broken down into smaller components or intermediate goals. For example, in solving a math puzzle, the model identifies the key operations or subproblems required to reach the solution. Step 2. Generating thoughts. At each step, the model produces several possible intermediate thoughts or actions. These thoughts could be partial solutions, hypotheses, or plans that guide the next steps. Step 3. Evaluating states. Each thought, or node, is evaluated for its promise toward achieving the goal. Evaluation can be summarized into two parts. Heuristics, assigning scores based on plausibility or alignment with the goal. Self-reflection. Models can critique or justify their reasoning, improving accuracy. Step 4. Exploring paths. Classic algorithms like breadth-first search, BFS, or depth-first search, DFS, are used to navigate the tree. BFS explores all thoughts at a given depth before moving to deeper levels, ideal for exhaustive reasoning. DFS focuses on one path deeply before backtracking, suitable for problems with fewer potential solutions. This structured exploration ensures that alternative possibilities are not prematurely discarded, unlike linear methods. Step 5. Selecting the best solution. After exploring multiple paths, the most optimal solution is selected based on accumulated evaluations and scores. This is the formal search algorithm described in the research paper. Unique features of iterative thought process. TOT mimics how humans solve complex problems by iteratively generating, evaluating, and revising thoughts. Parallel exploration. Unlike traditional methods that follow a single trajectory, TOT keeps multiple potential paths open, enabling robust decision-making. Heuristic-based filtering. 2T uses heuristics to prune less promising paths early, saving computational resources while maintaining focus on viable options. Experiments and results. T wasn't just a theory, it was tested against formidable tasks. Game of 24. Solve a puzzle using 4 numbers to achieve 24 with arithmetic operations. While GPT-4 with simpler strategies succeeded only 4% of the time, TOT achieved a staggering 74% success rate. Creative writing. Generate a coherent story ending with 4 given sentences. TOT's deliberate planning produced more cohesive narratives, outperforming both direct output and chain of thought (KOT) prompting. Mini crossword. Solve 5x5 crossword puzzles based on clues. TOT achieved a word-level success rate of 60% compared to just 15.6% with traditional methods, showcasing its prowess in iterative problem-solving. This is the comparison graph of the exact impact made with TOT from the research paper. How? By combining exploration, evaluation, and adaptability, TOT enabled the model to deliberate over possibilities and pursue the most promising solutions. TOT the answer? Performance gains. The framework has shown dramatic improvements in tasks requiring deliberation, planning, and backtracking, such as solving mathematical puzzles, Game of 24, and creative writing. The experiments demonstrate a clear advantage over KOT and I/O prompting, especially for complex reasoning tasks. Interdisciplinary foundations. By drawing on cognitive science models of dual-process reasoning, System 1 versus System 2, TOT effectively integrates fast, heuristic-based reasoning with slower, deliberate processes, improving decision accuracy. Scalability. Although computationally intensive, TOT offers modularity and flexibility, allowing users to balance performance with computational resources. Is TOT important? The Tree of Thoughts, TOT framework is revolutionizing the capabilities of large language models, LLMs, unleashing a new era of intelligent problem-solving. By empowering models to think strategically, TOT enables breakthroughs in tackling complex challenges once thought beyond AI's reach. Its modular and flexible design adapts effortlessly to diverse tasks, LLM architectures, and varying resource constraints, making it an indispensable tool across industries. Most thrillingly, TOT brings us closer to AI that mimics human-like deliberation, opening doors to real-world applications in robotics, creative coding, and high-stakes decision-making. With TOT, the future of AI isn't just about intelligence, it's about transforming how machines reason, adapt, and innovate in the world around us. What could go wrong? TOT requires significant computational resources, and its heuristics need refinement for greater efficiency. As tasks grow more complex, the framework must evolve to handle even deeper and broader problem spaces. A Turing machine, TM, can be used as a theoretical framework to analyze the complexity of the algorithms in the Tree of Thoughts, TOT framework, as it provides a formal model for computation. 1. Representation of TOT in a Turing machine. A Turing machine can simulate the TOT framework by mapping its key components into formal constructs. Input. The problem or task to be solved, e.g., a mathematical equation or planning task, can be encoded as a string for the TM. States. Each node in the Tree of Thoughts, representing a partial solution, corresponds to a state in the Turing machine. Transitions. Moving between nodes, e.g., generating new thoughts, evaluating states, can be represented as transitions in the TM, governed by rules encoding the heuristics or search algorithms used in TOT. Tape. The tape can store the problem state, intermediate thoughts, evaluation results, and outputs. By modeling TOT in this way, its computational steps can be analyzed in terms of the number of transitions required to solve a problem, which relates to the time complexity of the algorithm. 2. Complexity analysis. The complexity of TOT depends on several factors, which can be analyzed using Turing machine concepts. Search space size. In TOT, the number of nodes in the search tree, states in the TM, depends on the branching factor B, the number of thoughts generated at each node, and the depth D of the tree. A Turing machine simulation would iterate over these states, resulting in a complexity of approximately O(bxd) for exhaustive search. Heuristics evaluation. Heuristics in TOT prioritize certain branches of the tree. The computational cost of these evaluations can be represented as additional transitions in the TM, which could be OH, where H is the time to evaluate a single state. Combined with the search, the overall complexity becomes OHBRD. Search algorithm. The choice of search algorithm, e.g., breadth first search, BFS, depth first search, DFS, or A, directly affects the number of states explored and transitions required. BFS or DFS can be simulated with linear tape operations, but A introduces additional overhead for maintaining and querying a priority queue, affecting the space and time complexity. 3. Insights from Turing machine analysis. Upper bound. Using the TM model, the worst-case time complexity of TOT corresponds to exploring all nodes in the tree, which is O(bxd), akin to other tree-based search algorithms. Lower bound. With effective heuristics and pruning, the number of states explored can be significantly reduced, potentially making the complexity closer to OK, where K is the number of nodes actually visited. Space complexity. The space complexity depends on how states are stored and backtracking is managed, which could be analyzed by modeling the TM tape's usage. While a Turing machine is a helpful theoretical tool for analyzing algorithmic complexity, practical TOT implementations use real-world computational models, e.g. Python programs, GPU-accelerated processes. These add overheads like memory usage, parallelism, and data access times, which are not directly captured by the TM framework. However, the TM model still provides valuable insights into fundamental limits and scaling behavior. Extensions to computational classes. If we analyze TOT's computational requirements through a Turing machine, we can also position its complexity within broader computational classes. If the problem being solved by TOT is in non-deterministic polynomial time, AGI satisfiability problems, the complexity of the TM simulating TOT might be exponential unless effective heuristics are used. For highly complex tasks in exponential class with large search depths, TOT simulations could fall into exponential time. Optimization of heuristics. TMs can help analyze how heuristics affect the effective branching factor, potentially moving the complexity closer to polynomial in practical cases. The future calls for collaboration between algorithms, researchers, and even users like you to refine and expand the potential of tree of thoughts. Other ways? There is another way to achieve self-consistency and enable AI to perform with critical thinking skills. Self-reflection. Reflection is a framework that equips language models with dynamic memory and iterative self-feedback, enabling them to evaluate, refine, and adapt their reasoning processes. By integrating a memory system to store intermediate steps and outcomes, reflection allows models to recall past reasoning, identify errors, and avoid repeating mistakes. It operates in a feedback loop where the model critiques its outputs, generates self-feedback, and iteratively refines its solutions to meet the success criteria. This process enhances error correction, adaptability, and reasoning accuracy, making reflection particularly useful for tasks like debugging, complex problem-solving, and interactive applications. These approaches focus more on improving solutions within a single thought trajectory, rather than exploring multiple parallel paths, as in TOT. What is the future? Could it be a better integration with real-world applications? TOT's ability to mimic human-like deliberation opens doors to complex, real-world applications such as robotics, autonomous systems, and dynamic resource allocation. By enabling LLMs to plan, backtrack, and adapt to evolving scenarios, TOT could power critical domains like autonomous exploration, emergency response, and advanced decision-making systems in logistics and healthcare. Could it be a better multimodal and retrieval augmented reasoning performance? Expanding TOT to handle multiple modalities, e.g. text, images, audio, and integrating retrieval augmented generation would enable AI to tackle even broader tasks. Applications like visual question answering, interactive robotics, and multi-source data analysis could benefit from this evolution, allowing AI to reason across diverse inputs and access external knowledge in real time. Another trend could be resource-efficient and personalized. AI future iterations of TOT will likely focus on optimizing computational efficiency through smarter search algorithms and adaptive heuristics. Combined with the ability to personalize reasoning frameworks to users or organizations, TOT could become a cost-effective solution for tailored problem-solving, enhancing its scalability and accessibility across industries like education, customer service, and personalized healthcare. Closing thought. The Tree of Thoughts approach is a leap toward creating LLMs that don't just guess, they think. The Tree of Thoughts, TOT framework, marks a significant advancement in AI reasoning, enabling large language models, LLMs, to approach problem-solving through deliberate, structured processes. Unlike traditional token-by-token generation, TOT evaluates multiple reasoning paths, explores alternatives, and backtracks as needed, mimicking human-like deliberation. This approach dramatically improves LLM performance on tasks requiring strategic thinking, planning, and creativity, making it vital for applications in robotics, decision-making, and scientific discovery. Despite its strengths, TOT faces challenges such as computational inefficiency, as exploring large search trees can be resource-intensive. Additionally, its reliance on heuristic evaluations makes performance highly dependent on the quality of heuristics, which may not generalize well across all tasks. There is also a trade-off between exploration depth and time constraints, limiting its scalability in real-time applications. Furthermore, integrating TOT with external systems like retrieval or multimodal reasoning adds complexity. The future of TOT lies in addressing its computational challenges and extending its capabilities. Enhancements like adaptive heuristics, dynamic pruning, and end-to-end trainable TOT models can optimize its efficiency. Integrating memory systems will allow TOT to build on past interactions for long-term reasoning. Its application could expand to real-time decision-making in robotics, personalized AI assistance, and complex problem-solving in fields like law and medicine. Additionally, combining TOT with retrieval-augmented generation, RAG, and multimodal systems could enable it to reason across vast knowledge bases and diverse input types. Ultimately, TOT represents a critical step toward artificial general intelligence, AGI, laying the groundwork for AI systems that think, plan, and adapt like humans. While TOT excels at deliberate reasoning, alternative methods offer complementary strengths. For example, reflection equips LLMs with iterative self-feedback, enabling refinement within a single reasoning trajectory. This approach reduces computational loads by focusing on narrower paths or leveraging hybrid systems. What do you think could be the best approach? Leave your comments below. The journey has just begun, and with innovations like TOT, the horizon of what LLMs can achieve is expanding exponentially. Together, we are shaping the future of intelligence. Are you ready to explore the branches of possibility? Share your experiences in the comments below. Don't forget to like, subscribe, and hit the notification bell for more insights on AI prompting and content creation.